All right, guys, it's Mrs. Roderick. This is Forces in Motion. My guys, go to your Chapter 11 notes in your binder, page 23A, and I want you filling in the blanks as we go so we can run through this quick tomorrow and kind of move forward. So first thing, we're talking about forces. A force, you probably remember from elementary school, it's just a push or a pull that acts on an object. It can cause a resting object to move, or it can accelerate a moving object. Remember, we talked about acceleration last chapter. That could be speeding up, slowing down, or changing direction. Forces, the unit of measurement is a Newton. You want to memorize that. Just like mass is grams and distance is meters, the unit for of force is going to be a Newton. So we'll say Joey pulled with 5 newtons of force. That's your label or your unit. Just to give you an idea, Newton is the force that causes a 1 kilogram mass to accelerate at a rate of 1 meter per second squared. So we'll look at some examples in class so you guys can kind of get a feel for this. But I really want you to wrap your brain around this, memorizing these units, that 1 Newton is equal to a kilogram times a meter per second, or sometimes we make it simple and say a meter per second squared. So we'll have to use that with some problems that we get into a little bit in the future, but that's not for today, so you guys will be cool. All right, so we use arrows to represent forces, and the arrow will tell you the direction and the strength of the force. The longer the force, this is a bigger force than this. And we can combine forces. A net force is just that overall force acting on an object after you combine all those forces. So some forces might be together, like if you're a running back and you're pushing on a blocker, the two of you added together, you might say you have you're a force of 2 newtons and they're a force pushing on you with 2 newtons, so that equals a 4 Newton force in that direction. You can also have subtracting forces. We're going to talk about friction today, and a subtracting force would be, if you're pushing in one direction, friction always opposes motion. So if this was 2 newtons and this was 5 newtons, your resulting force would be in this direction, 3 newtons. So equal and opposite forces are gonna result in no movement, because it'll be 0. So that's pretty easy to understand. So forces in the same direction get added together. Forces in the opposite directions you subtract, and whichever direction that it's going in, that's going to be the direction of the force. So the idea here is you have balanced forces and unbalanced forces. Think of tug of war, think about arm wrestling. Balanced forces are when you combine the forces, you get a net force of 0. So, if I'm pushing with 2 newtons this way and you're pushing on me with 2 newtons that way, neither of us are going to move. That's a balanced force. And then an unbalanced force is when they're not equal. So it doesn't equal 0. So one person is pushing more. I push with 3 newtons, you only push with 2 newtons, we're going to get movement in this way of 1 newton. So again, think about tug of war, think about arm wrestling, that sort of thing. So balanced versus unbalanced forces. You have to have an unbalanced force to cause motion. All right, so friction. There are 5 main types of friction. Remember, friction is just always a force that opposes the motion. So if you take your hand on your desk or wherever you're sitting right now and you move it one way or the other, that force you feel against you from allowing you to slide, that's friction. The first type of friction we're going to talk about is static friction. Static is just the friction that holds objects that are not moving. So on your table right now, you probably have some books or maybe a lamp or something, and it's staying there because of static friction. If you want to move those, you push on that book, you have to overcome static friction. It always opposes the applied force. Like I said, try to move something that won't move, or things sitting on a table without falling off. That's static friction that you're overcoming. And static friction is always the strongest friction. If you guys can think about moving something, it's always harder to get something moving than once you get it going, to kind of keep it moving is easier. So that's your static friction. The next type of friction is sliding friction. Exactly how it sounds, these little polar bears sliding across the ice. Sliding friction is just any time you have two surfaces that are sliding past each other. If you're trying to, slide a box across the floor, that's sliding friction. And it's always going to be less than your static friction. Like I said, it's easier to keep something moving than to start it moving. Static friction is high. There's a lot of friction. It's hard to overcome. Once you get something sliding, it's a little bit easier. So sliding friction is less than static friction. And what's even easier than sliding something is put it on a dolly, put it on a cart and roll it, because rolling friction is really a lot less. Anytime you're, the friction force that acts on rolling objects is called rolling friction. And it is 100 to 1,000 times less than sliding and static friction. That's why I can move a refrigerator if I have it on a cart or on a dolly. I can move some heavy things. Ball bearings that are in your skateboards and your rollerblades and things like that, those reduce friction a ton, because instead of having surfaces sliding past each other and rubbing against each other, you have these little spheres which are going to reduce that surface area that's touching a whole lot. So we'll take a look again at these tomorrow in class. The next one is fluid friction, and the term fluid actually means anything that flows. So air and gases are fluids, as well as liquids like water. So fluid friction is just that force of friction that opposes motion of an object through a fluid. So, and like I said, a fluid is any liquid or gas or mixture of those. Air resistance, we think about air resistance all the time. Tons of people do a lot of work trying to reduce air resistance, make things aerodynamic, is to reduce your air resistance. So anytime you're talking about friction between air and an object, that's air resistance. You look at this car, this double-decker bus, lots of air resistance, lots of surfaces that the air is hitting there. Not very aerodynamic. But then look at this sports car, that's very aerodynamic. Not as much friction with that air against there. And then the second type that I added here, and I really want you guys to add this to your notes, so I should be able to check this tomorrow and see that you added all this stuff and as well as filled in your blanks, is drag. And drag is fluid friction with water. Any of our swimmers, I know our swimmers went down to state today, they talk about reducing their drag, reducing the friction with them and the water. Maybe you saw some of the guys shave their heads, or then they even shave their bodies to reduce the hair on their body, to reduce that drag or that friction with the water. Boats are made very aerodynamically to reduce that drag or that fluid friction with water. All right? We'll come back. I'll take a look at that tomorrow. The last thing I want to talk about today, and this is what we'll work on in class a little bit tomorrow, is gravity. We talked about gravity last chapter. Gravity is just a force that acts between any two masses. It's an attractive force, meaning that things are pulled together. And gravity depends on two things, mass and distance. The bigger the mass, the stronger the gravitational attraction, and the closer the distance, the stronger the gravity. There's actually a formula you'll do in physics we won't do now. So we used these acceleration formulas last chapter when we talked about, car accelerates from 0 to 60 in 2 seconds or whatever. But now we're going to talk about it dealing with falling objects. So if I ever say we drop something, or something is falling or free falling, I want you to memorize this number, 9.8 meters per second per second. That's the acceleration due to gravity on Earth, okay? And we'll assume, if I don't tell you any otherwise, that we are on Earth. So you can assume we're on Earth, and so the acceleration due to gravity is 9.8 meters per second per second. So gravity, of course, causes objects to accelerate down, whereas air resistance acts in the direction that opposes that, and that reduces the acceleration. But we're always going to ignore air resistance and just talk about everything accelerates at 9.8 meters per second, or meters per second squared. So what we're going to be solving for is usually either time or final velocity, or maybe initial velocity. But if I don't tell you otherwise, if I drop something, my initial velocity would be 0. Okay, I'm holding it in my hand. I'm going to let it go. It's my initial velocity, unless I tell you otherwise, will be 0. My acceleration will be that 9.8 meters per second per second. So a lot of times I'll ask you for the final velocity, like what's the velocity right before it hits the ground, or how long is it falling? And then this term terminal velocity, that's just the constant velocity. Basically, if you drop something, and you've probably heard, you can kill someone if you drop a penny off the terminal tower. It is going to be going pretty fast if you're accelerating at this rate. But eventually, from really high up, things reach what's called terminal velocity. So instead of speeding up, eventually it stops speeding up. It keeps moving at a constant velocity, and that's called terminal velocity, where your air resistance and that force or acceleration of gravity is kind of balanced out. So let's take a look at some problems. So I want you to get out a clean sheet of notebook paper and a pencil and a calculator. And we're going to do these two problems. I'm going to do number 1 with you guys right now, and then I want you to do number 2 and bring it to class tomorrow. One problem, do the problem and bring it to class tomorrow. Just like always, same process. You read your question. If I drop a water balloon, so as soon as you see the word drop and they're saying that it's falling down, we know that our acceleration is that number we memorized, 9.8 meters per second, or 9.8 meters per second squared. And it says, so I drop a water balloon out a window and it falls for 2.85 seconds. 2.85 seconds is the time. I'm hoping you're saying these out loud at home. All right. Again, that's how long it's falling. Units for time, seconds. You should be able to figure that out. And then it says, how fast will it be going right before it hits the ground? So we're looking for how fast, we're looking for a velocity, and right before it hits the ground, that's going to be your final velocity. And like I said, if I drop a water balloon, before I drop it, what is its initial or its starting velocity? It's in my hand. I'm holding it. It's 0 meters per second. All right. That first step is huge, being able to tell those. So let's go ahead and write our formula. VF, get it off the front. Hopefully you can do that algebra, but it's kind of tough. A times T plus VI. And then we'll say our VF equals our A, which is the 9.8 meters per second, times our 2.85 seconds, and then plus our 0 meters per second. So if you get out your calculator, 9.8 times 2.85 is 27.9. I rounded it to just 3 sig figs there, 1, 2, 3. And seconds on bottom cancel seconds on top, plus the 0 meters per second. Our answer is 27.9 meters per second. All right, so take a look at that. You have your formulas on the other page, and I want you to answer number 2 and come to class with number 2 done. Great job, guys. I'll see you in class. Let me know if you have any troubles.